Let us look at proposition number 7 of works of Archimedes, specifically from on conoids and spheroids. The proposition says, given an ellipse with center C and a line CO drawn perpendicular to its plane, it is possible to find a circular cone with vertex O and such that the given ellipse is a section of it. So let's see how we can arrive at the cone. Given an ellipse with major axis A prime and minor axis B prime. Now it may look as if the BB prime is the major axis, but it is not. It is tilted. So that's why it looks like that. So let me just show it to you. So if you notice that the AA prime is the major axis. Draw OC perpendicular to the plane of the ellipse. Produce OB, OC and OB prime. OB, OC and OB prime. Draw a line from B in the plane BOB prime intersecting extended OC and extended OB prime at E and D such that B times ED is to EO square is equal to AC square is to CO square. So let's draw that line. So we draw a line such that it intersects these two lines, OC and OB prime, in such a way that this proportion is applicable. BE times ED is to EO square is equal to AC square is to CO square. Draw a circle with BDS diameter in the plane perpendicular to the plane BOB prime. So let's draw the circle. Now remember, this circle has been drawn in the plane perpendicular to the plane BOB prime. So here we have this plane and this circle has been drawn in this plane. Draw a cone with circle on BD as the base and O as the vertex. So let's visualize the cone. This is a point on the circumference of the circle whose diameter is BD. So as you notice, a cone has been formed of which this ellipse is a section. Now you might have noticed that this is not a right circular cone. It is a cone which is called a oblique cone. Now we have to prove that if we take any point on this ellipse and we extend the line joining O and that point and extend it to the circle, it would be a straight line. So take any point P on the ellipse. Now take any point P on the ellipse and drop a perpendicular on BP prime. Let's say it drops at N. Now join ON and produce it to meet BD at M. So we join ON and then we extend it so that it intersects BD at M. Draw MQ in the plane of the circle on BD as diameter perpendicular to BD and meeting the circle at Q. So what this means is we draw a perpendicular from BD to the circle on BD and we mark the point at which it touches the circle as Q. Draw a line through E parallel to BB prime. And let's mark these points as F and G. Similarly, we have to draw a line HK to M parallel to BB prime. So let's mark this as H and this as K. QM square is equal to BM times MD. Since QM is perpendicular to BD and BQM is a semicircle on BD. So what this means is we can form these triangles. And this is the semicircle. So we have seen previously, comes from Euclid elements, that QM square is equal to BM times MD. Now let's divide QM square on the left hand side and BM times MD on the right hand side by HM times MK. HM times MK. Now, QM square is to HM times MK is equal to B times ED is to BFE times EG. Now, how did we get this? Because remember, BM times MD is equal to QM square. Similarly, we can draw a perpendicular ER on BD, in which case we end up with RE square is equal to B times ED. Here, since it is the same semicircle and HK is parallel to FG, that means the ratios will remain same. That is, the ratios BM times MD is to HM times MK will be the same as B times ED is to FE times EG. So again, here also we can draw these and visualize it. QM square is to HM times MK is equal to B times ED is to EO square times EO square is to FE times EG. So what have we done here? We have divided B times ED by EO square and EO square we have divided by FE times EG. So it is the same as multiplying this ratio by the ratio EO square is to EO square. E times ED is to EO square is what? Is AC square is to CO square. So we can substitute that. And similarly, EO square is to FE times EG. EO square is to FE times EG can be written as CO square is to BC times B prime C. Why? Because BB prime and FG are parallel to each other. That means these ratios will remain the same. B, in the triangle FOG, BB prime is parallel to one of the sides of the triangle. We can substitute EO square is to FE times EG by CO square is to BC times B prime C. Now, here we have CO square and here we have CO square. So these two will cancel out and we'll end up with AC square is to BC times B prime C. Now, QM square is to HM times MK is equal to PN square is to BN times NB prime. Because again, you see, this is AC square is to BC times CB prime. Same semicircle. If we look at NP, PN square is equal to BN times NB prime. And since it is the same semicircle, the ratios will remain same. So alternately, we can say QM square is to PN square is equal to HM times MK is to BN times NB prime. Again, using similarity of triangles, we can say HM times NK is to BN times NB prime is equal to OM square is to ON square, which means QM is to PN is equal to OM is to ON. So what does that mean? It means that since this Pn is dividing OM in the same ratio as QM is to Pn, we can say Pn is parallel to QM, which means if we join OP and PQ, OPQ is a straight line, but Q is on the circumference to the circle on BD. So that means OQ is a generator of the cone, which means the cone passes through all the points on the ellipse. Because we had taken P as an arbitrary point on the ellipse. So we have found a cone whose section is the given ellipse. And we have proved that all the points on the ellipse lies on the surface of the cone. That was proposition number 7 of works of Archimedes, specifically from on conoids and spheroids. Again, let me remind you, there is a link to a PDF book which describes all these propositions in detail. Please feel free to download it, refer to it, and if you think somebody else can also benefit from it, please do share. That's it for now.